If you've ever felt like you're drowning in the alphabet soup of modern tech, CPU, GPU, TPU, and all the rest, you are definitely not alone. These acronyms, they're the engines powering, well, pretty much everything, from your phone to the entire AI revolution. So let's break it all down and figure out what they all mean and, more importantly, why we need so many of them.
This is really where the story begins. Back in 2012, this model called AlexNet pretty much kicked off the deep learning explosion we see today. Fast forward to now, and we've got these absolute behemoths like Gemini. The progress has been incredible, but it's also created a huge problem. Our need for computing power is growing at a rate that is just mind-boggling. And yeah, all this incredible progress with AI, it comes with a hefty price tag, an almost bottomless hunger for processing power. A hunger that is pushing our current technology right to its breaking point.
And here's the core of the problem. For decades, computers have been built on something called the von Neumann architecture. Now, the key thing to know is that the processor and the memory are separate. For AI, which has to shuttle massive, and I mean massive, amounts of data back and forth, that little pathway between them turns into a giant traffic jam. It's a bottleneck that the old designs just can't handle efficiently anymore.
So, how did we first try to solve this? Well, we turned to a pair of processors that most of us are probably familiar with. Let's call them the classic duo that really powered that first big wave of the AI boom. First up, you've got the CPU, the central processing unit. Think of it as the brain, or maybe the general manager, of your computer. It is a master of all trades, designed to handle one complex instruction after another, right in a row. It's perfect for things like running your operating system or figuring out the fastest route on a map.
And I love this analogy because it just perfectly captures the difference. A CPU is like a Toyota Camry. It's reliable, it's super versatile, it gets you through all your daily tasks. A GPU, on the other hand, well, it's a rocket ship. It's unbelievably powerful for one very specific job, going ridiculously fast in a straight line, but you wouldn't exactly use it to run to the grocery store.
This difference really comes down to how they're built. A top-of-the-line CPU might have, say, 16 or 24 really powerful complex cores. But a modern GPU, we're talking somewhere around 10,000 simpler ones. See, the CPU is built for complex, one-at-a-time logic. The GPU is built for massive parallelism, doing thousands of simple calculations all at the exact same moment. And it turns out that this parallel processing power is exactly what deep learning craves. Training an AI model means doing millions, even billions of calculations all at once. It's a job that GPUs were basically born to do. And that's why they became the must-have hardware for the AI revolution. Suddenly, you could train these huge models in days instead of months. It was a complete game changer.
But even the mighty GPU started to show some cracks, especially when it came to how much power it consumed. As AI's appetite just kept growing, the industry had a realization. A one-size-fits-all approach just wasn't going to cut it anymore. It was time for a new evolution, hyper-specialized chips built for very, very specific jobs.
And that brings us to the TPU, the Tensor Processing Unit from Google. Now, this is not a general-purpose tool. It's an ASIC, an application-specific integrated circuit. It was built from the ground up to do one thing and do it better than anything else: the core math that powers deep learning, the kind of tensor operations that give it its name. And wow, does the performance tell the story? Check out these benchmarks from a recent study. A GPU took 300 seconds to train a model. The TPU sliced that time in half. The DPU did it in a quarter of the time. That right there is the power of specialization. But hold on, speed is only half the picture. Take a look at the energy use. That GPU burned through 1.44 megajoules in an hour. The TPU used less, but the DPU, it's on another planet. These specialized chips aren't just faster for their jobs, they are ridiculously more efficient. And when you're powering a massive data center, that is everything.
That brings us to our next specialist, the DPU. And this isn't some minor player. I mean, NVIDIA's own CEO called it the third major pillar of computing, right up there with the CPU and GPU. So, what's the big deal?
The DPU is basically the logistics expert, the traffic controller of the data center. Its whole job is to manage the flow of data. It takes all the networking, storage, and security grunt work off the CPU's plate. This frees up the CPU to focus on what it does best, running applications, while the DPU handles all the complex data traffic. The whole system just runs faster and smoother.
So, we've gone from generalists to specialists. But what if the next step isn't just a different kind of specialist?
What if it's a completely new way of thinking about computing itself? Well, that's where we get into the quantum leap.
Okay, so every processor we've discussed so far, CPUs, GPUs, all of them, they all speak the same basic language, classical bits. It's a world of ones and zeros, on or off, yes or no. But the QPU, the quantum processing unit, it operates in a whole different reality. It moves from bits to qubits.
So what on earth is a qubit? Well, this is where things get a little weird, but stick with me. Instead of just being a 0 or 1, a qubit can exist in what's called a superposition. It can be both at the same time. And through another Wilds property called entanglement, the states of two qubits can be linked, no matter how far apart they are. This lets QPUs explore a staggering number of possibilities all at once, making them perfect for solving problems that are just flat out impossible for classical computers. We're talking about discovering new medicines or designing revolutionary materials. But there's a dark side. A powerful enough quantum computer running an algorithm like Shor's could, in theory, break most of the encryption that protects our digital world today.
All right, that was a whirlwind tour from the familiar CPU all the way to the mind-bending QPU. So let's pull all these threads together and figure out how to choose the right tool for the right job.
Here it is, your quick and dirty cheat sheet. The CPU is your go-to versatile workhorse. The GPU is the king of doing a million things at once, but man, is it power hungry. The TPU is a genius at AI math, but it's a one-trick pony. The DPU is the master traffic cop for data centers. And the QPU, well, it holds incredible promise for the future, but the hardware is still very much in its early days.
So, the most important thing to take away from all this is simple. We're moving past the idea of having one single, all-powerful processor. The future of computing isn't about finding one champion to rule them all. It's about building a team of specialists, a diverse toolbox where every single processor is perfectly designed for its unique role.
And this massive shift from a single generalist to a whole team of experts, it just opens up so many incredible possibilities, which leaves us with a final, really exciting question to think about. With this powerful new team of specialized processors all working together, what problems that seem completely impossible today are we going to solve tomorrow?